Yes.
So good evening everyone, and apologies for the slight delay in the start of the session. This is yet another live session for the course Mapping DSP Algorithms to Architectures. So what I'm planning to do today is primarily, I think there were a few questions that had been raised on the discussion forum, as well as in the feedback on what should be discussed more. The main thing I would like to do, I think there is some confusion on how data flow graphs can be used, and how we should go about doing the analysis of that. So I'm basically going to take the assignment for week 2 and go through that, and time permitting, maybe we can do that for week 3 as well. I think some of you had also asked for can detailed solutions to the assignments be given. I have tried to give feedback for the assignments along with the answers that are provided over there, but I can also go through those and try and give additional clarity if something is not, in particular if you have any specific doubts about what is not quite clear about it. Okay, so what I will do right now is very quickly sort of review what we mean when we talk about a data flow graph. Right. The important thing to keep in mind over here is where is it that we use data flow graphs, and what is it that we are trying to convey by means of this data flow graph, right? To sort of put it very simply, the sort of simplest form of data flow graph would probably have just two nodes, right? A to B. And what we mean is this is doing some function or computation, right? And B is doing some other computation, right? Now these computations that I'm talking about could be as simple as just an addition or multiplication or something like that, or they could be more complex. A, for example, might be doing a complete FIR filter structure, or B might be doing a complete some kind of an image processing application. So the level of granularity, in other words, what exactly is being done inside A and B, are not specified in the data flow graph. They could be fine-grained, literally additions, gate level operations, or coarse-grained, meaning that fairly complex multi-clock cycle computations that are being performed inside this. Okay, and the crucial thing is this arrow over here, which indicates dependence. Okay, in other words, if I have an arrow from A to B like this, effectively what it says is B depends on A. Okay. Another way of putting it would be that I cannot start the computation of B until I have got the output generated by A. So that is essentially the essence of what is being conveyed by this data flow graph. Okay, and that is the main thing that you need to keep in mind when you are trying to understand what is the purpose and use of this data flow graph. So now in the case of, so how do we take this further? Supposing I have a data flow graph which is or rather one edge in a data flow graph which is indicated by something like this, right, where I have basically said that I have a computation A, a computation B, and there is this D which is a kind of a delay element, right, which is basically, I can think of it as one sample delay, right? What I mean by sample delay is A is producing samples at its output. Now that those samples could be simple numbers, or it could even be an entire image, a frame of an image of a video could be one sample, for example, right? In which case a sample delay would be the previous frame, not just the previous pixel, right? You could also think of it as sort of being some kind of a register or storage, right? But this is can potentially be misleading. It sort of gives you the impression that we are talking about, single bits or small values over here. So probably delay element or sample delay are the best ways of really thinking about what this D means. What does it mean in practice? It basically means that a given, now over here basically what it says is B depends on A as before, but the previous iteration of A. Okay, which means that we need to be very clear about what exactly we mean by iteration and how do we sort of decide what is the previous iteration of a particular computation. Okay, so that essentially brings us to the notion of iteration, and what we can say over here is if I have a single node, then effectively what I can think of is it has any signal processing system has multiple iterations, right, which I would basically call as A0 is the very zeroth iteration, or the first zeroth iteration. A1 would be the first iteration, A2 and so on, right? Effectively infinite duration, right? What I mean by infinite duration is because these are signal processing systems that are working with samples of data, there is no actual termination or end to how many times this particular computation can happen. As an example, an FIR filter, right, continuously takes input samples and generates output samples. Right? This is something called a non-terminating process. Right? In other words, there is no concept of saying when does the FIR filter finish. As long as input data samples are present, the FIR filter has some more work to do. Okay? It will have to generate the next output data. So that is the sense in which I mean this is a non-terminating process. And why I am saying that, this basically corresponds to sort of infinite duration sequence. Okay. All right. So if I have this concept that the A0, A1, A2, etc. are a continuous sequence of output of iterations of this particular function, right? Effectively what I am saying is that I need to continuously keep on generating output samples. Okay. So then what does that mean? I now have A over here and I have B. Okay. Effectively what I can say is A0 generates some output data, this will be consumed or used by B0, right? In other words, the zeroth iteration of B, right? And similarly A1 generates some output, this will be consumed by B1. Okay, and we go on like this. Right. So in terms of this A0, A1, etc., the operations that are actually happening, right, what I can think of is there is a sequence of steps that is happening. So A0 happens first, then A1, then A2, then A3 and so on. The question is, when does B0, B1, B2, etc. happen? Okay. Now let's say that I have only a single processor, single processing element, right, on which function A and function B have to be executed. Okay. then what I can do, for example, is A0, A1, A2, right, would effectively create 3 output samples corresponding to A, which means that after I have done this, B0, B1, B2 can execute. Okay. And in other words, this sequence is a so-called valid sequence of execution, right? The terminology that is used is A and B are actors, A0, A1, A2, etc. are invocations or firing instances of A, and similarly B0, B1, B2, etc. are invocations of B. Okay. So A0, B0, A1, B1 is an example of a so-called firing sequence, right? So just like I said, A0, A1, A2, B0, B1, B2 is a valid sequence of execution. A0, B0, A1, B1 is also a valid sequence of execution. Another term for it is firing sequence. Okay. So with all of that in mind, what we can now see is that effectively, so I've already seen 2 examples of what are valid sequences, right? But A0, B1, for example, is invalid, right? Why? B1 depends on A1. It cannot execute before A1. Okay. So I actually need to be a bit more precise over here. I should probably say A0, B1, A1 is invalid, right? Because otherwise I have not really specified when A1 executes at all. Similarly, saying something like A0, A1, B0, B1, B2, right? At this point it becomes invalid. Everything else was okay, right? And so in other words, it's possible to generate pretty much any sequence of these numbers, which you could say either it's valid or invalid. A1, A0 is also invalid by its very nature, right? Essentially what we are saying is A1 executes before A0, but that's just by definition not possible. By definition what I'm saying is the 0th time it executes is A0, the next time is A1, and so on. So it doesn't even make sense to sort of talk about A1, A0 as a possible sequence, right? So this notion of sort of creating firing sequences is very useful to understand the behavior or evolution of a data flow graph, which is essentially what sort of the assignment 2 question 1 is dealing question 2 is dealing with, right? An example, so in order to take that particular example, what we have over there is A, there is another function B, there is another function C. There are 2 delay elements over here, but a dependency back from B to a single delay element here, and a dependency back from C to A. Okay. So the simplest way of sort of looking at this is just a data flow graph. Can I create firing sequences for it? Okay. So in order to understand what are valid firing sequences, right, the thing to keep in mind is, in the previous example, what I had was I could always sort of fire A anytime I wanted. So A0 did not have anything else that it depended on, Okay, I could just start it off. Similarly, after A0 is done, the next one A1 also, I did not have to wait for anything before it could fire, right? But if I want to sort of go in here and say, how would I let me just insert a new page before this. If I want to ask the question, how would I deal with a situation where A and B have a dependency of this sort, right? This basically implies B depends on A. Can I have something like this? A, B, and B to A, right? In other words, what this is sort of saying is B depends on A, yes, so far so good, but A also depends on B. There is a problem here, right? This is effectively something called a deadlock. What it's saying is we don't know which one to start. A cannot start until B has completed, B cannot start until A has completed, so neither one can start and we cannot proceed further over here, right? At a superficial level, one way that you can think about this is very similar to the notion of why we say that combinational loops are not permitted in combinational logic circuits. Okay, it is not exactly the same thing, so don't sort of take the analogy too exactly, but it is closely related, the reason why we cannot do this thing. So how do we break this? How can I have a situation where, you know, I have a function, I have a pair of functions like this, A depends on B, B depends on A. The only way I can do it is if I say that, all right, if I have something like this, which basically says A is required before B can execute and B is required before A can execute, but there is a delay element out here, right? What does the delay element say? Effectively what it says is, now A depends on the previous iteration of B, right? Which means that if I write out my dependencies explicitly, what I'm sort of saying is, from A0 I have a dependency to B0, but from B0 I have a dependency to A1, not to A0. Okay, so that is valid. Now after A1 has executed, I can then go on and execute B1, right? And after B1 has executed, I can then go on to execute A2, right? This part of it, the B0 to A1, is the previous iteration dependence. Similarly, B1 to A2 is also previous iteration dependence. Okay, and because it depends on the previous iteration, it suddenly, you know, all the sort of causality violation that, or the deadlock that we were worried about, has gone away, right? Because after all, I compute A0, then I compute B0, and after B0 I can compute A1. So effectively what I'm saying is A0 did not have a dependency on B0. A0 had a dependency on something else, which is the previous iteration of B, which, what would that be? That would be basically be my B minus 1, right? Which we are sort of capturing in the form of this. I can think of it as an initial condition. Right? Something like B minus 1. Okay. So how does that help us? It basically says that if I had something like what I have in assignment 2, question 2, this means that this is an initial condition which basically corresponds to B minus 1. Okay. And this is also initial condition, right? A minus 1 and A minus 2 are both present, are both available. Right? So how does that help us? Effectively what it's saying in other words is, if I consider just the edge A to B with 2 delays on it, right, I could have a firing sequence which is B does not have to depend on anything else, right? In this case, of course, in fact I have this loop over here. Now A0 cannot execute until B0 has completed, because there is a direct edge back from B to A. Okay, but on the other hand, B0 can execute, right? It depends effectively on A of -2. Similarly, B1 can also execute. And after that, what I have is, once B0 has executed, A0 can execute, right? And once B1 has executed, A1 can execute, right? So this is the dependency from B0 to A0, similarly from B1 to A1. Okay. After that, what I have is, can I do A2? No, because that requires B2 to have executed. But can I do B2? Yes, because it turns out that this is the condition that needs to be satisfied. B2 can execute only after A0 has executed, right? Effectively what this is saying is, Bn depends on A n minus 2. Okay, which means further that I can go forward like this and say that A1 means that B3 can execute. Then I can do A2, A3, B4, etc. Okay, because what would happen is that I effectively have from B3 I can go to A3, from B2 to A2, B3 to A3, and then from A2 to B4. Okay, this is the Bn depends on An minus 2 link that I have over there, right? Is this the only possible firing sequence? Of course not. I could also have had another valid sequence which would look something like, I still have to start with B, so B0, but as soon as B0 has completed, I could straight away run A0, right? And after that, I can then basically go ahead and run B1 and then A1, B2, A2, B3, A3. This is also valid. Why? Because the B0 to A0 dependency is directly there, B1 to A1 dependency is there, A0 to B2 is required over here, right? And similarly, A1 to B3, okay, B2 to A2, B3 to A3, right? But after that, what I have is A2 would then have a forward dependency to B4 and so on. Okay, so in other words, both of these are valid firing sequences. What is an example of an invalid firing sequence in this case? B0, B1, B2, A0, right? This violates Bn depends on A n minus 2, right? I am trying to do B2 before I have done A0. It's a violation of the constraint. Okay, so with this in mind, effectively what we can see is, how do I decide the various kinds of sequences that we had over there? Just quickly redrawing this for convenience, right? The first question was A0, B0, C0, right? Question is, can A0 fire at the beginning? And the answer is basically no. It depends on, sorry, I've got the diagram wrong over here. This should have been 2D over here and D over here, not like this. Yeah. With this diagram, what I have is that A0 depends on B0 and on C0. Both of them. You will see that there are two edges out here. Right? So until both of them have been taken care of, A0 cannot execute. So straight away A0 is a dependency violation. Right? What about the next sequence, which was B0 B1, C0 C1, and then A0 A1? Right? Is this a valid sequence? What are the dependencies that we have to take care of? Right? A0 depends on C0 and B0. So both of these are okay. Right? Similarly, A1 depends on B1 and C1. Okay? C0 actually depends only on B minus 1. Similarly, C1 depends on B0. So this is also sort of taken care of, and so C1 does depend on B0, but that's also a forward direction. So there are no problems over here, right? All the dependencies, in other words, that we can think of in this case are all taken care of, right? So all dependencies are okay over here, valid, and this is a valid sequence. What about the third option that we had as part of the question? It was basically saying C0, C1, B0, B1, A0, A1. Okay. Now let me look at C0. Does it have a dependency? Yes, on B of minus 1, right, which is available. So it's perfectly okay. Right. What about C1? This depends on B0. Right? And because B0 happens only after C1, I've effectively had a dependency violation at this point. Okay? Okay. So this is basically how you can sort of construct this kind of firing sequences and check for their validity. Okay. Now, a related question was to do with the question of what is latency, right? So what is the latency of a particular sequence of computations, right? And if I look at the sequence, like this, right? Effectively what I have is latency is defined as one iteration, one full iteration from start to the finish of that iteration, right? So in this case, for example, B0, C0, A0 is one iteration. Right? This would be an example of one iteration. Now, the point is I cannot directly do B0, C0, A0 because this depends on B. That's actually fine. There's no further dependency here. So B0, C0, A0 is actually fine as one iteration, right? It could have been executed on its own and it would be one complete iteration. Now, in this case, the problem that I have is B0, C0, A0 is not being executed directly in that sequence. I have B0, B1, then C0, C1, and then A0. So from the start of B0 to end of A0, the total latency that I have is going to be equal to, in this case, what do I have? I basically know that the dA and dB are equal to 10 and dC is equal to 40, right? So effectively what I have in other words is B0 10 time units, B1 10 time units, C0 40, C1 40, A0 10. Completed iteration 0. And total latency is equal to 110 time units, whatever that is. Okay. Now there is one specific point that I want to raise over here, which is related to how latency is defined, right? I think one question that was in fact raised on the discussion forum was, for an FIR filter, or rather if I have a large number of delays on an edge, then shouldn't I be taking that n number of delays also into account while defining the latency of the end-to-end latency? Now the reason why I'm not doing that and I'm just going ahead with just sort of saying, okay, from the time required for one complete iteration, rather than whether I'm specifically saying that I'm also considering the number of delay elements on it, is because we are primarily interested in the measurement of latency purely from the implementation point of view, right? We are looking at it as VLSI designers, and therefore we are primarily interested in, from the implementation point of view, at what point can I basically repeat this computation. Okay. If I take that as my definition of latency, then I don't really care about the fact that I have a large number of delays sitting between the A and the B edge. Okay. So this is more of a sort of practical definition of latency rather than the literal definition of latency as in terms of what it would be for a FIR or FIR filter or something of that sort. Okay. So please keep that in mind. I mean, our definition of latency is basically whatever is required for us to be able to construct a valid schedule and to then be able to repeat it as we move forward. Okay, so that is how we end up with this number 110 units over here. Okay, the related question over there would basically be the initiation interval, right? So in terms of initiation interval, basically what we can say is I have the time between iteration 0 to iteration 1, right? Delta t is basically just 10 time units, right? But that's not really a good measure of my initiation interval, because what I need to consider over here is B0 to B2 is going to be 120 time units, right? Why? Because if I go back and look at this graph, then basically what I'm saying is I have B0, B1, C0, C1, A0, A1, and then B2, B3, etc. right? So this time is basically going to be equal to 120 time units, right? Similarly, if I follow the same pattern over here, then the time until essentially B4, for example, can start over here would be another 120 time units, right? And within this time, 2 iterations have executed. Okay, similarly over here I have another 2 iterations. So basically what that tells me is the average initiation interval is going to be equal to 120 sorry, I've got these numbers wrong. This will, I think I have a small issue that I need to check over here. So this would basically be 120 time units. Yeah, which would basically mean that the average II is going to be equal to 120 divided by 2 is equal to 60 time units. Okay, so let me just double check this. I believe this might be in fact something that I need to check on the answer that was provided over there. We'll be re-evaluating the assignment. I will just confirm this and send out a discussion post to confirm this particular problem over here. But effectively what we will have is, this is how you could compute the average initiation interval, right? The simplest way to think about it is, in the steady state, as you undergo a large number of iterations, what is the average time that I'm going to spend between successive complete iterations? That would be a good way of defining the initiation interval. Okay. All right. So I'm going to leave it there as far as assignment 2 is concerned. I just want to also very quickly take a look at some questions from assignment 3, right? What we have over there is essentially looking at cycles in the graph, right, for the purpose of computing the iteration period. Okay, and what we have over there is the example that we took was essentially this one, which has a B something form of essentially an IIR filter, right? Okay, so some kind of a system that looks like this. Keep in mind, this is more of a block diagram than really a data flow graph, right? But on the other hand, nominally this is exactly the same kind of structure that we would have in a data flow graph as well, right? The important point over here is, once again, whether we have this block diagram or whether we have something else which is closer to our structure of what we would draw as a data flow graph, at the end of the day, the main thing that we need to keep in mind over here is each of these edges is sort of showing a dependency, right? This is a dependency on previous iteration. This is a direct dependency. This is a dependency on previous iteration. Why? Because of this delay element over here, and similarly this delay element over here. This is again a direct dependency that we have, right? So all of these edges that I have basically shown marked in red, which show dependencies, those need to be taken into account, and as discussed in the lecture, we can write down timing constraints corresponding to each of these edges. Okay, what we will end up with as a result of doing that is that we will have, finally the constraints can be accumulated over cycles, and you would end up with a certain set of cycles that you need to take into account when you are trying to find the average iteration period. One such cycle would be this one, and the other such cycle would be this longer one out here. Okay, so these two cycles that I have marked, one in magenta and the other in light blue, are essentially the things that you need to take into account when we are trying to find the average iteration period. So in the list that I have, basically if I write down the list of nodes, what I have is a cycle starting at node A, going to B, then going to D, C, and then back to A is one of the cycles that I need to take into account. That is the one marked in light blue, and the other one is just the one that basically goes B to D to B, a small cycle. This is the magenta one, right? Okay, so these two cycles are the ones that I can basically use in order to compute the iteration period of this system, right? If I actually do the computation, what I end up with is that t is greater than or equal to, in this case it would be t of an adder plus t of another adder, well, let me see, t of b plus t of d plus t of c divided by the total number of delays, right, which basically if I actually plug in the numbers over there, time through an adder is 1, time through a multiplier is 2, so it will become 1 plus 1 plus 2 plus 2 divided by 2 is equal to 3 nanoseconds. And similarly in this case it would be t is greater than or equal to td plus tb divided by 1 plus 2 by 1 again equal to 3 nanoseconds. Okay, so this is an example where both the cycles effectively had the same sort of cycle mean through them, right? But what can be done by means of this computation is that you can find out an overall average iteration period bound, and in this case, of course, in both cases it comes out to be 3 nanoseconds, but that tells you that that's the minimum time required between successive iterations of this particular filter. Okay, as long as you are restricted to using adders that have a propagation delay of 1 nanosecond and multipliers that have a propagation delay of 2 nanoseconds, there is no way that you can get to less than a sample period of 3 nanoseconds. Okay. Yeah. One last thing which I am going to consider now, basically based on the questions, not questions, but on assignment 3, is with regard to cut sets used for retiming, right? So just to go over the idea of retiming very quickly, effectively what we have is, supposing we have a data flow graph like this. Okay, what we are saying is, I mean, this is a very trivial version of a data flow graph. So effectively what I'm saying is that if I just wanted to cut the graph into 2 parts, right, and add a delay element over here, this is a valid pipelining, right? And this is an example of what's called a feed forward cut set, right? If it's valid pipelining, automatically it is also valid retiming. There is no problem with that either. Okay. What if my data flow graph was something slightly different? It essentially had something like this. In other words, B, and also some other dependency from here to another edge C, and then merging back over here. Okay. Now what I can have is, this could be a valid pipelining feed forward cut set, right? Why is it a cut set? Because by removing these 2 edges that are marked, the AB and AC edges, I have divided the graph into 2 parts with no edge directly going across from one side to the other, right? And at the same time, what I have over here is all the edges that were removed are always going from one side of this cut to the other. That's what I mean by a feed forward cut set. Okay. Another example of a feed forward cut set for the same thing would be this one. This is also a valid pipelining feed forward cut set. Okay. So what is not a valid pipelining feed forward cut set? Let's take the same diagram. Right? If I take this, for example, right? So edge A to C, edge C to B. Okay. One way that you can sort of visualize this is then to say, okay, let me draw this clearly, right? Now A and B need to be on one side of my cut, C is on the other side. Okay, I have basically applied a cut set over here, right? What were the edges that went across the cut? One from A to C, the other one from C to B. Okay, the 2 cuts are in opposite directions. Okay. The simple thing to keep in mind if you are having cuts that go in opposite directions is, if I am, let's say, adding a register on one of the edges and the other edge is going in the opposite direction, I should be able to subtract a register or a delay element from that edge. That's the simplest way of thinking about it. In this case, I cannot. This is not a valid feed forward cut set, and also not valid for retiming. Right? So that probably requires a little bit more explanation. What is the difference between pipelining and retiming? It is simply that, like I said, if I have an edge that is going in the opposite direction of the one that I expect, then I should be able to subtract a delay element from there, and if that works, then it is a valid cut set for retiming. Okay, let's consider the same graph but with a slightly different structure. Right? What if it had one delay element over here? Okay, and now I take this cut set and say I'm going to do retiming across this. Okay, what would the cut set look like? Essentially, I would have A and B over here, C on the other side, the cut set. A to C is an edge in this direction, C to B is going in the opposite direction, right? C to B originally had one D over here, right? But what I'm going to do now is to say that I'm going to do, let's say, +1 over here and -1 over here. Okay? What would that result in? I would get A, B, C on this side, draw the cut set, draw these two arcs. But now what has effectively happened is I now have +1, meaning that there is a D over here and nothing on this side. Okay, or to redraw the graph in looking like the previous one, what I have is A, B, C, one delay on the edge A to C and no delays on the edge A to B. Okay, this is a retimed version of the graph at top of the page, right? Why do we call it retiming? Because effectively that delay element has been pushed from the edge C to B back to the edge A to C, and as a result of doing that, it effectively changes the timing at which changes the iteration dependence of A on C. In other words, previously C depended directly on A from the same iteration. Now what we are saying is C now depends on A from a previous iteration. On the original graph, B depended on C from the previous iteration. Now B depends on C from the same iteration. So the timing of the way that A and C and B now depend on each other has been changed slightly, hence the word retime. Okay. The example that was given, or rather the question that was given in the assignment, sort of asks you to do the same thing. It basically says, let's look at A, 2 delays going to B, 1 delay going to C, edge from C to A and edge from B to A. Okay, and in this case the question is, what happens if I try to take a cut set like this. Okay, so this is basically the x1 cut set. Okay, how can I make this valid? By essentially saying I will do +1 delay over here, +1 delay over here, and -1 delay on the A to B edge. Why is this valid? Because I already have 2 delay elements on the A to B edge, which means that subtracting 1 is possible. I won't go into a negative number of delays. Okay, what will end up happening is that I will get a resulting graph that looks like this. The number of delays on A to B would have gone down to 1. The number of delays on B to C remains unchanged. The number of delays on B to A goes up by 1, and the number of delays on C to A also goes up by 1. This would be the new structure of the retimed graph. Okay, so this is how we can sort of come to the conclusion that the x1 cut set is a valid cut set. Okay, and similarly, what we can basically do is, check the others, x2, x2, x3, x3, and so on, and find out which of them are valid and which are not valid. Okay. All right. So I think what I had done now was basically gone over some of the questions that were related to assignment 2 and assignment 3. Okay. And hopefully that has helped to clarify some of the questions that you had with regard to data flow graphs, what it means to talk about firing sequences, how they can be used in order to sort of validate the dependencies, and also to compute the latencies as well as the initiation interval, right? And also a little bit about what does retiming mean, retiming and pipelining, and how that can be applied on a data flow graph. Okay, so I'll stop here for now because there haven't been any other questions raised at the moment, and we can feel free to ask questions in the discussion forum, and we can basically take it forward from there and continue the discussions either on the forum or in another live session later if required. All right, thank you.